many countries for the business and work purpose such as Australia, Japan, France, USA, Qatar, Indonesia, UAE, and Malaysia. He has contributed several metro and high-speed rail projects globally such as High Speed to London, UK, Geelong Fast Rail Australia, R151 Singapore, RRTS India, Etihad Rail UAE, Dubai Metro Extension and Dubai Expo Link UAE, WSR UK, R2P Germany, WDFCC India, LR3 Kuala Lumpur Malaysia, Jakarta LRT, MRT Indonesia, Network Rail UK, Delhi Metro, Line 8 India, Doha Metro Project Qatar, Sydney Metro Australia, Hyderabad Metro India, Invensys Rail USA and UK. He has to credit his several research papers, articles, and patent. Also authored a book, Early Software Reliability Prediction, a fuzzy logic approach. Dr. Kumar is currently serving as working as technical principal RAMS Mott McDonald, Bangalore. Sir, over to you.
Thank you, Professor, for a nice introduction. I'm audible. I'm audible to everyone. Okay, wonderful.
Yes.
So let me share my screen. And so screen is visible, correct? I will switch to slide mode in due course. Okay. So just to take the advantage of bandwidth, I will be switching off my video. It's okay, sir? It's mandatory to keep on video on. Professor Vivek.
Yes, sir.
I'm telling, should I switch off my video so that we can take advantage, or should it on? What do you recommend?
No, it's up to you. If signal strength is okay, then you can keep it on. If you are facing any trouble, you can please switch off.
Okay, just okay. Okay, so good evening, everyone. Formally, so I will be spending around 2 hours for this system reliability modeling. Before starting this, I assume, and I attended also some of the lecture earlier, that basic concept of reliability engineering has been covered, correct? And it will be very great support from all the faculty members and other participants if they can support me by giving some answers and interacting. So then course will be very interesting. Okay, so somebody can tell basic reliability engineering concept has been covered earlier. Yes or no? Correct?
Yes, sir.
Yes, sir. Wonderful. So, Professor Vivek, 2 sessions has been done, reliability engineering basics.
Yes, sir. Monday and Tuesday, both the session delivered by the Professor N.K. Goel. Okay. And he has covered the introduction of the reliability engineering, and in the second section, he covered reliability mathematics and the probability theory.
Oh, yeah, wonderful. Okay. So anyway, I will also touch a few concepts just to in the different tone, so that there should be not missing information. And to start with this whole course has focused on the reliability engineering. And when we talk about reliability engineering, and as reliability engineers, we always think about failure for any systems. Yesterday, I was also listening Professor Goel. Your car fail, your automotive fail, your TV fail, anything fail. So failure of any system, either it is mechanical, electrical, electronic, software, civil, any system will fail. So just I want to start this my session. Why any system fail? Then we will go to the real engineering, because I can understand the audience in this forum are from different backgrounds. Somebody from electrical background, somebody from software background, somebody mechanical background as well. So any system fail. So why system fail? What is the fundamental cause of failure? Then we will go to the modeling, and I will lightly touch upon the basic principles. So anybody can help me just to understand why you think anything fails. Suppose you are from mechanical background, you tell me whatever thing. Why any system fail? Please.
Sir, from the learnings we have received from you in last session in NIT, I will say it's like what we could learn is when the system is been stressed,
Yeah.
stressed to a limit more than for what it has been designed.
Yeah, correct. Wonderful. So in simple way, every systems has been designed for certain strength, some power, either mechanical or electrical or anything. If we put more stress, okay, which if I designed, it will fail. If you design a mechanical system for some load, if you put more load, it will fail. Similarly, if you design an electrical system for some voltage, if you give more voltage, it will fail. So the fundamental things is system will fail if the put more stress than its strength. And second thing, if we always keep our stress lesser than this strength, it will fail or not.
Excuse me, sir.
Yeah.
Your screen is missing. The PPT you have to put on share.
I just share.
Yeah, it is visible now. Yeah, thank you.
Okay.
Thank you.
Okay. Okay. Wonderful. Thank you, Professor. So, suppose if you give stress always below the strength, it should not fail. Suppose you design for any system for 20 volt, if you give 10 volt, it should never fail. But even though it's fail, correct? Because things has been not designed for the lifetime. So things will also fail because of its aging effect. Because with respect to time, the system strength is decreasing and it's going to fail. So two fundamental fail. First is the gap between strength and strength, and second because of its wear and tear. Anyway, I think some noise is there. Somebody can take care of this. Okay. So I will run this slide very fast because it has been done earlier. Okay. So everything you need reliable and safe product. Everybody wanted some reliable and safe product because things fail. From washing machine to signaling control system, anything you think, thing will fail. Okay. So an average customer, suppose we are a general customer, are aware about the concept of reliability. Everybody is very light mode, light term. Everybody is saying system is not reliable. This is not reliable. What actual meaning? It is not properly understood. So average customer are aware the concept of reliability, but not perfectly. Organizations are aware the cost of unreliability, and manufacturer focus on the cost of failure during the warranty. So see, organizations are aware the cost of unreliability. This is very important term, very relevant today also. As a company, they are always evaluating if system fail, what will be the cost. And you take any system. Let us take some few examples from today also. Have you heard that the many companies like Toyota has recalled so many cars from so many cars because of some anomalies, or some Nokia has recalled many batteries, and leave it all those things. Recently, have you heard about the Chat GPT? Correct? For only one error in their software, I think $100 billion or $1 million lost the company. Just it is last week it happened. So because the software is not properly designed and the software could not answer one thing. See how much loss. So cost of failure is very important. So one is the cost of failure, and apart from this, there is another subject. Everyone needs the reliable and safe. Safety is another subject. That is, I will not cover, but I'm telling you. So one is the cost, one is the life. There are many software, there are many systems are designed just to working in the safe environment, like avionics, nuclear power. In that case, safety failure will not impact cost, but also impact the life. So the whole area we call RAMS, RAMS, reliability, availability, maintainability, and safety. So this subject is very wide, and this is a very good forum. At least we are getting to understand what is the reliability, how to model, how to design, what is the impact. So when we talk about RAMS, there are two branches, RAM and safety. Safety is a different branch, and maybe down the line, maybe I can request the professor to organize similar kind of course on the safety engineering. That is a complete different forum, different pillars. Here a complete focus on the reliability. Okay. So why do engineering products fail? There are many things: designing, quality construction, human error, gap, aging effect. There are many things. And if all the failure we classify in two categories, in engineering terms, we are classifying these things as systematic failure and random failure. So failure can be classified in two branches, systematic and random. Systematic means if you design any product, whatever your engineering, maybe mechanical system, electrical system, electronic system, if you design any product and from requirement analysis, design, integration, manufacturing, testing, okay, so every stage is some V cycle. Okay, let me put the pointer here so that it will be easy for you. Okay, from here, step 1, step 2, step 3, there are many cycle, many steps. Okay, or sometimes in it we call the V cycle. From requirement, then design, okay, then integration, something. So every step, certain principle has been designed. How to collect requirement, how to do design. Designing means primarily design, detailed design, then final design, then how to design interface, how to integrate. So during the product development life cycle, if you do any mistake, it means you have done certain kind of error in the requirement or design or any place. So we call the systematic error. And if your product is having systematic error, definitely it will going to fail, not today but tomorrow. So systematic failure means systematic error. Random means system has been designed, there is no systematic, but because of certain wear and tear, certain over voltage, certain kind of unexpected condition, okay, for which it has not been designed, we call random failure. So when you are developing a product, either you're developing a mobile, either you're developing a railway systems, you are testing your product to ensure that there is no systematic error and there is no random error. So the question comes here, how to ensure that our system is systematically correct and how to handle if random error happen. So it's a very good question. Random, because random error, even though product is very good, suppose I have a mobile, okay, very good. I have a car, no problem, everything perfectly fine. But what can go wrong? So to handle random error, all the critical systems, for example, suppose signaling systems, there are 2-3 signals are there. If one signal fails, one will take over. Like aircraft, there 2 or 3 engines are there. If suddenly one engine fail, another engine will work. So random failure are managed through redundancy, some standby solution. Systematic failure, we have to do certain guidelines and principles and standards. So as engineers, whatever your discipline, either mechanical, electrical, electronics, every engineering having certain principles and guidelines and standards. If you follow those guidelines, standards and principles during your design and development, it means your systematic development is correct. You are designing your product systematically correct. And since there is a possibility of failure, it's a probability of failure, and system is very critical. You design for the some standby system to handle this. So in this way, your whole system is the reliable. Okay. So this is the starting point of the reliability. So outcome is systematic failure and random failure. We must be considered during our product designing. If system is fail, we are saying system is not reliable, unreliable. So in this session, we are going to study how to evaluate the reliability of system. Okay. So this is the system reliability modeling. How to model a system, okay, where we can evaluate its reliability. So the impact of failure varies from minor inconvenience to significant economic loss and death. Yes. Legally, manufacturers are responsible for most of these failures. That is why concept of chargeable failure warranty and DLP. So nowadays, since reliability engineering and safety engineering so mature, so there are some legal liabilities imposed on the manufacturer. If your product fails, you have to give some money, some warranty, some DLP. DLP is for the defect liability period. In the rail industry, we are doing the DLP. Up to 2 years, if something goes wrong, you have to replace without any cost. So this again, reliability, 3 terms has been defined by earlier. The probability the system will perform the required function, period of time, and operating condition. It means required function, period of time, and operating condition. So reliability, 3 keywords. What is the function you wanted? What time and what condition? Suppose I say reliability of this product is the how much? It is not correct question. The reliability of this product is on 10 hour, 100 hour, 1 year, 2 year. That is the correct definition. So reliability is always a time parameter. So reliability of a product at t is equal to 0 is 1. And reliability of the product at t is equal to infinite is the 0. The reliability vary from 0 to 1. If you don't use the product, reliability is 1. Okay. And infinite time, it will be, it means with respect to time, reliability will be decreasing. So again, I will not spend time here. Required function, different systems have different functionalities, like railway, like automotive, like your mobile. What function you design for that? It should be perform those functions. If it is not performing those functions, things are unreliable. Time, for what time you design, and condition, under what condition. This is very important in the industry. In the industry, it is very, very important. Suppose you design a motorcycle and the reliability is this much, but condition is your speed should be not exceed 60. You have to replace your filter after 10,000 or 4,000 kilometers, some conditions. So if your system, you are maintaining those conditions, then reliability is the 98%. So for any systems, if you design and you're selling to a market, you're putting some condition, and those conditions you should maintain to achieve those reliability. And this is for everywhere. Okay, suppose you design a train. I'm from train expert, and track has been designed for running the train for the 100 kmph, and you're running the train more than 100 and it failed. It's not failure, because this track and train has been designed for the 100 kilometers. And if you're running the train more than 100, it will fail. So that failure is not failure. So this is very clear understood. For every system you design, whatever your branch, you specify the condition, under what condition it should be used. And that's why reliability. If you violate the condition, definitely this is not a reliability issue. Okay. So why reliability engineering? I have already spent many things. We want everything to continuous working. In today's technology world, everyone depends upon the continuous functioning of the wide array of complex machinery equipment. We expect our car, computer, everything should run on time without failure. When they fail, result can be catastrophic injury. It's very Moreover, repeated failure is a very important point. Repeated failures leads to inconvenience, annoyance, and lasting customer dissatisfaction. So, if you are repeating the failure, sometimes if failures are repeating, it means there is a systematic failure. Very important point. If suddenly something fail one time, random failure, it's okay. But if failure are repeated, it means there is systematic failure. It takes long time for a company to build up the reputation for reliability, and only short time to be branded as unreliable after shipping the flawed product. The same thing happened with Google GPT. See, Google takes years to make the very good company and very good product, but in one day something fail, people are saying like that. So, continual assessment of new product reliability and ongoing control of reliability, everything shift are critical necessity in today's competitive business area. Means reliability is required for many reasons: satisfaction, cost of failure, company branding, competitions. So, after certain time, all the product, all the batteries, all the car, all the motorbikes, all the TV, all the laptop, all are same. I am using the Dell laptop, you are using HP laptop. All functions are same, but where the companies are differentiating their product, it is the reliability. My product is so reliable, my replacement is so easy, my repair time is less, my MTBF is this. So reliability is, there are many reliability matrices. On the basis of this, reliability gives the some kind of differentiation to promote the product and compare others, that this product is different from others. This is the why reliability engineering. So that's why I have taken this kind of survey from one of the book. Okay, and survey has been done in some. In this poll, 100 individuals were interviewed, and the question has been asked, ranking 10 attributes on a scale from 1 to 10. So what they're saying, how you are buying the product, what is the key factor, what attribute you are selecting to buying a product. Somebody saying performance, somebody saying last long life reliability, somebody saying service, somebody saying maintainability, somebody saying warranty, age of use, appearance, brand value, packaging, display, latest model. So see, these are the, see, even you can think yourself, if you are buying any product in Amazon, anything, new mobile or new anything, camera. So these are the attributes we are comparing. And among these attributes, see, till here, all are reliability attributes. It means somehow, directly or indirectly, we can translate in terms of reliability. So reliability is the core of any product, which can make this product different from others. Okay. So why reliability engineering? It is one of the most growing field. Okay, and that's why this course has been organized, because now we are going to make many product through Make in India program, and we have to see what we are going to make in India program, many products. Definitely those products are existing by other countries, other brands. So we as a faculty, as an industrialist, we should understand the importance of reliability, and so that we can compare our product are reliable and safe. So unreliable product often has safety and health hazard. Reliability values are used for marketing and warranty purpose. Nowadays, most of the contract are specifying reliability requirement. Any industry, I worked in 3 industries: railway, automotive, and avionics. None of the contract is without reliability requirement. Public awareness, public are well aware about reliability. If something goes wrong, they put in the social media and feedback and all these things. Earlier, there are no such awareness. Profit considerations resulting from high cost of failure, like this Chat GPT. There are many lists of this kind of failure. They repair warranty, standardization by regulatory agencies. there are many regulatory agencies, okay, they are putting some kind of regulations. You develop this product with this kind of standards, you guidelines, okay, without this product will be not approved. So these are the reliability engineering introduction. So reliability engineering attempt study, characterize, measure and analyze the failure repair systems in order to improve their operation by use of increasing design life, eliminating or reducing the fault and reducing downtime. So this is the whole theory. Now I'm sure that you understand what is the importance of reliability engineering, and moreover this reliability engineering again is another branch or another super specialized skill is the safety engineering, where we focus only on the safety aspect. Okay, I can help you here. In reliability engineering, we want to a product failure free, but in safety engineering we want to develop a product in the mishap free, risk free, hazard free. It means if that product fail, that fault occur, something safety impact will be on the health or on the life. So reliability and safety goes in parallel. Okay, in some industries they take the precedence of safety engineering over reliability engineering. So relationship between quality and reliability. So quality and reliability and safety, three things are there. Safety, I can explain you. Safety means, suppose if you have a system here, a product, and in product there are many failure, 1 2 3 4 5 6, they are the fault. Okay, you take about software point of view. Suppose you are software guy, these are the bugs. So in these bugs, if this fail, 1 2, if this 2 fails, there may be some safety because some hazard will happen, but remaining this fail, some inconvenient will happen. Let me take another simple example from my industry, rail industry. Suppose you are traveling in the train or metro train. Okay, let's take car example also. Okay, you are driving a car. Okay, what happened? Suddenly your music system fail, or your horn is not working. Okay, so some sound is coming in your car, some noise is coming. These are the failure. These are the reliability failure. But your car is running, suddenly your brake system fail, brake is not working, steering alignment is not doing proper, or gear may be not running properly. So these are the failure. This failure may cause the safety impact. In railway example, in metro, train is running, suddenly announcement gone, light gone, AC gone. It is a failure. But this failure will cause inconvenient, not the safety impact. But when train is running and suddenly door open, metro door, it is a safety failure. So safety is a different branch that I will not covering, but safety is a safety failure is subset of reliability failure. Some of the fault may more critical fault, and that's why we call the safety failure. In quality, in simple way, reliability depends upon the time. Okay, reliability, quality in time domain we call reliability. Okay, so quality and reliability, see, reliability will be impacted by product design and by the process used in the product manufacture. Once a reliability product is designed, quality engineering techniques are used to make sure that process produce the product. It means, suppose you design some kind of circuit here. Okay, some PCB you design. Okay, some PCB you design here, and as per some principle saying this PCB is very good reliable. This PCB is a very good design. So now, as a reliability engineer, you have designed a good PCB. Now it is a duty of quality engineer to make sure proper quality process has been followed to make this product reliable. Your design is good, but you have used the substandard material. Your process is not good. You are not able to proper soldering. So these are the quality flaws. Your design is good, but product is not good because of there is quality flaws. Correct? So quality techniques are used to make sure that processes produce their product. Okay. Quality and reliability engineers provide different input in design process. Different input. Quality engineers suggest change that permit to the item to be produced within the tolerance at reasonable cost, and reliability engineers makes recommendation that permits the item to function correctly for a longer period of time. Once an item has been successfully manufactured, suppose you develop a mobile, okay, the traditionally quality assurance function has completed. Suppose you develop a mobile, you have given to through quality process is done. So one product has been manufactured through quality process, quality job done. But reliability functions focus on what happened next. Means, are the components failing prematurely? You design for 2 years and it failing in before that. Was burning insufficient? Is a constant failure? It means reliability. Reliability is the lifelong process. The quality is one-time process. You achieve quality, job done. Data collection, reliability data is the after the component has been produced and manufactured, because you are running a car. Mean time to failure, mean time between failure, mean time to repair, how many times it failed in 10 years. So once product has been manufactured, you are using in the field, those data we wanted. But quality engineering during the manufacturing process. There are many difference between quality and reliability. Quality and reliability, quality, reliability and safety. So quality, okay, in safety, failure behavior means all failure. Reliability means all failure. And safety means dangerous failure. Analysis nature. In reliability engineering, we focus on what system are supposed to do. This should do, this should do. Our mobile should run, our laptop should run, our washing machine should run. But safety, what system is not supposed to do. For example, if your microwave oven door is open, it should not on. So oven should not operate if door is open. Washing machine is not operate if something got stuck. Because safety issue. In safety engineering, they always focus what system are not supposed to do if something goes wrong. Goal nature. Safety engineering is a lot of application industries. Okay. And once you understand the reliability engineering properly, the next maturity level go to the safety engineering. Requirement nature. Formal definition, I skip it. This definition has been done by earlier. Meantime, reliability, availability, maintainability. Reliability has been quantified in two ways: MTBF and MTTF. Mean time between failure. Professor Goel has been covered. Mean time to failure. Okay, both are same. Okay, failure rate and MTBF both are reciprocal. Okay, MTBF is equal to 1 by failure rate. I think this has been covered. Okay, 1 by lambda we called it. 1 by lambda. That is the MTBF. Okay, MTBF. Okay, MTBF is equal to 1 by lambda. So failure rate, MTBF, MTTR. So this formula has been already covered yesterday, and just to again recap it, here you have see MTBF is MTBF or MTTF equal to 1 by lambda. MTTF is for the non-repairable system. MTBF is for the repairable systems. Again, this formula, though it has been covered, but I would like to again recap it in very simple way. Availability is the MTBF plus MTTR. Okay, where MTBF is the 1 by lambda and MTTR is the 1 by mu. If you solve this, it will come. So there are three kinds of availability: inherent availability, achieved availability, and operational availability. So in relevant terms, or in any manufacturing process systems, I can explain you what is the inherent availability. Inherent availability means design availability. Okay, design availability. Before you go for design availability, let me focus on the repair time. Okay, repair time. What is repair time? Suppose you're running a car, okay, and suddenly in your car some switch damage. Okay, let us say horn is failed. Horn is not working because some switch is failed. So what you will do? You will go to any. Suppose you have spare horn, you spare switch in your car. You go and put and do it. It will take hardly 10 minutes to you. But replacing time may be hardly 5 to 10 minutes. Okay, just to open and replace it. A repair time also, if something has been gone, you can repair it 5 to 10 minutes. But suppose if you driving car on the highway, you are very away from the service station, then you have to inform, product have to come, it will take time. So what I want to convey, one is the repair time, actual repair time, we call the MTTR, mean time to repair. Okay, but sometimes in repair time requires actual condition, the restore time, because when system got restored, suppose your washing machine is failed, something gone, so when you inform the service station or your internal staff, he will come, he will replace, he will restore. The mean times, the actual time is 10 minutes, but total time is the 1 hour. So restore time is the complete 1 hour. So we call it the operational availability. Operational availability means total time it takes. In rail industry, we are following the operational availability, because suppose something goes wrong in the train, so we inform the station master, door is not working, or brake has failed. Somebody will come, they will give permission. Okay, then some formality is there. So we can see here mean downtime corrective maintenance, mean downtime preventive maintenance, mean downtime admin delay. So during repair for any product, there are many time occurred. One time is the actual repair time, second maybe restore time, third maybe some kind of admin time. So total time. So your system is not available because of any reason. Okay, so that's why inherent availability means I know a register replacing will take 5 minutes. The mean time actual inherent, mean time to repair, but this is unrealistic. This is ideal condition. This is ideal condition. Ideal condition. Mean uptime plus mean downtime corrective maintenance. So corrective maintenance is not realistic always. Okay, in industries there are many time involved to repair and to restore any product. That's why some kind of corrective and preventive maintenance, and some kind of time corrective, preventive, and so maintenance. Three kind of maintenance: corrective maintenance, preventive maintenance, and admin delay. If you sum all the maintenance time, then it comes the operational availability. Okay, so this is very important point and very realistic. The same thing in different availability point of view, we can skip. You can also see here downtime. Downtime is more intuitive way to understand the availability. How system is available? Better to think downtime. Suppose you have a mobile, you have a machine, availability is the 90%. And suppose your mobile is supposed to work how much? 24 hours, 365 days, correct? We are using mobile. Okay, so we wanted our mobile should be always online. So depending upon our product, what is availability sub calculate. So in your mobile case, 90% availability means 10% downtime. It means 10% 8760. It means this much downtime. It means if your mobile is 90% available in a year, for 1 year, it means this much will be not available. If your mobile is 99% available, it means 1% downtime. And this is this much hour you service, you can't use service in 1 year. In 1 year, 80 hours, around I think more than 3 days, you can't use the mobile. This is not acceptable. Suppose, see, the 99% looks very good value. Availability of my product is 99%. In say, in railway also, we can say our train is reliable for the 99%. Suppose 24 by train, some train. So see, 87 hours, 90 hours train is not available. That is not acceptable. 99.9, this much. So in rail industry, we always start from here. Minimum 99.99. It means this much. It means 1 hour, approximate 1 hour. 1 hour we can allow. 1 hour means in first month 5 minutes, in some month 20 minutes, in some month 30 minutes. Total 1 hour I can allow for my train to be unavailable. Okay, for corrective reason. So availability is very important point to understand from reliability point of view. This I have seen that Professor Goel has covered, bathtub curve. So bathtub curve has the 3 regions. Okay, early region, useful region. This you can see here, early regions. So burning, useful life, wear out, it has been covered. Okay, just want to touch here. In burning, what are the failure reasons? Why failure happen? Because of manufacturing defect. And how to improve this burning? Burning testing, screening, quality control, acceptance testing. In useful life, what is the reason? Environment, random load, human error. How to redundancy and this access strength. Because strength you put more. Suppose you design a system with more strength and you put less because derating. Okay, this is also useful life. Wear out. What is the reason? In wear out, what is failure happen? Wear out, failure happen because of fatigue, corrosion, aging, friction. These are the things. So how to handle this failure in wear out? Derating, preventive maintenance, part replacement. So every reason, some failure happen, and this failure, how to improve? These are the techniques. Okay. So after reading all those things, I have developed some understanding about reliability engineering. All the system product have finite life. Every system, nothing infinite. Some design life, we call design life. So how to design, develop and maintain the system product so that it lives its design life. Reliability engineering, what we are studying, we are not making systems to be infinite time. Our objective is, suppose we have designed a product for 5 years. We have to make sure it should run 5 years without failure. That is how we are engineering. So what is design life and how to meet and how to calculate design life because of failure rate. So that I will come in next topic. Suppose you make you give one PCB, one circuit, one transformer. You design some transformer, and how you can say this transformer design life is 10 years or 5 years. So that if you can predict or you can assess, then you can tell in the market my transformer will the 10 years warranty. If you can't do properly, if you can give 10-year warranty and all your transformer going to fail within 10 years, so our product comes to you and your company will be in loss. Root cause of failure between gap between the stress and strength. So, and this failure due to present a fault inside the system product, systematic, and failure due to the random failure. Reliability is 100% only if you don't use it. It means R at R0, RT is 1 and R infinite is 0. As the value increase, value of t increase, R start decreasing. It means if t tends to infinite, R tends to 0. MTBF is the inverse of failure rate. You can see I discuss here. MTBF is equal to 1 by lambda. It's very important understanding. MTBF is equals to 1 by lambda. MTBF is the inverse of failure rate, which can be used to calculate the reliability. I think this line is very important. Those who are attended the earlier lecture, you can correlate. MTBF is not reliability. MTBF is not reliability, but MTBF is the metric by which we can calculate the reliability. It is not representing reliability. Reliability of system at its MTBF is only 36%. So don't get confused with reliability. What does it mean? Reliability of a system at its MTBF is 36%. It means, suppose yesterday Professor Goel has covered, I was in the lecture, that I remember RT is equals to e to power minus lambda t. Correct? RT. So what is lambda? Suppose you have a product. Suppose you have one product A and you have one product B. Okay. MTBF of this product is the 3000 hour. 3000 hour. Okay. And for this is the 5000 hour. Okay. So what is the reliability of A at t is equal to 3000 hour? See, what is the reliability of A at t is equal to 3000 hour? So let us say A. Reliability of A at 3000 hours, let us say here MTBF is 3000 hour. So here we can say R, okay, and we put here T means 3000 hour. Okay, 3000 hour. I'm putting 3000 hour equals to, can calculate e to the power lambda. Lambda means 1 by MTBF, correct? MTBF is MTBF. It means 1 by 3000, correct? And T क्या है? 3000 into 3000. 3. So 3 cancel. Value becomes e to the power minus 1, which is the 36%. Similarly, if B, so reliability of any system at its MTBF is always 36%. So you can't say reliability of a system is 1 lakh hours. Okay, if MTBF is 1 lakh, 36% only. Okay. Redundancy does not increase reliability, rather than it increases availability. Redundancy, see, the very important point. Redundancy does not increase the reliability. Very important point. Please think again. Redundancy does not increase the reliability, but it increases the availability. For example, I'm taking one example of myself. I was in a meeting in railway project, and I asked my supplier to give UPS for my server room, because server room is very important. And I told this reliability of this UPS should be this much. Maybe I have given MTBF value, MTBF 10,000 hours. But he has given UPS, and UPS MTBF is coming around 8,000 something. I told your UPS is not reliable, because 8,000 something reliability becomes 96%. I want 99% reliability. So what he has given? Yes, sir, I agree. He has given two UPS, one UPS and two UPS like that, and put in the parallel. He's told if this UPS fail, this will take over. So your system becomes the reliable. Then I told no, my system is not reliable. I want reliable product. By putting redundancy, you can increase the availability. It is not reliability, because you are putting two systems. Who will pay the maintenance? Who will pay the space? Who will do other activities? So reliability means design issue. See, it doesn't means I'm having 4 laptops with poor quality. One laptop goes, I will do another laptop. It's not correct way. By putting multiple product, I can improve their availability, but I don't want. I want the reliable product. Correct? So this is the thing very important. What is reliability? What is availability? There are many failure pattern, reliability analysis, increasing failure rate, constant failure rate, decreasing failure rate. You can understand the bathtub curve. CFR is widely used. CFR is in the most case. CFR means constant failure rate. You can see here this figure. This is failure. This region. CFR. Because we wanted more. We are more concerned about the useful life. I have taken a mobile for 5 years. If beyond 5 years, no problem. Advantages, but till 5 years should not fail. My washing machine, my car. So that's why in most of the calculation we are using this formula, h power lambda, h power minus lambda t, and this h power minus lambda t only for this constant failure rate. Okay, this is not for the always. This is very important. Reliability theory cannot predict a product will fail, but it can predict about the population. Means reliability theory, complete theory, reliability for the population, not for the a product. Just to give you an example, I have purchased a normal tube light in my house, local, maybe simple, and you purchase the Crompton grip of Philips. And what happened? Mine is working, local, but your have failed. It doesn't mean that is my reliability is poor, your reliability is, my reliability is good, your reliability is poor. One product. What the best way? You purchased, you consider the thousands of local product and thousands of those products and run for some time and see the result. It means by one day some product fail, one time you do some mistakes, it doesn't mean you are not reliable. For reliability, we want the more data. That this is I want to say in different way. So reliability, for reliability analysis, reliability calculation, we want more data, more population, then only we can predict and assess the reliability. For one time, it's not. The reliability theory cannot predict when a product will fail. A single, but population. So reliability last, reliability comes on cost. Pay me now or pay later. All reliability engineering, all industries. Okay, as a reliability expert, I'm advising reliability comes on cost. If you want your product to be reliable, you must today give some analysis, hire some reliability engineers, do some studies. Okay, if you're not doing, no problem, not do today, but tomorrow you have to do. Okay, so this is the reliability comes on cost. This is my understanding on reliability. Okay, now we will focus on the system reliability modeling actual content. Okay, so what I can do, I can give the break as per schedule. I was advised to take a 10-minute break. Then I will come on the next topic, system reliability modeling, so that we can correlate all the concept. Why, how to calculate the reliability of a system. Okay.
Sir, one query if it can be taken, sir.
Yes, please.
Sir, like you just shared, no, sir, when we are talking about parallel system, we are improving basically the availability, not the reliability.
Yeah, very good. Yeah.
Sir, but when we talk mathematically, sir, if two systems are in parallel and then we do the mathematical calculation like 1 minus availability and then failure wala part. With that calculation, so sir, we are calculating it like it appears mathematically like reliability has improved when two systems are in parallel.
Yeah, you are right. You are right. I'm talking about the in general sense. See, in that way, you can see the reliability of whole system because system is available. Okay, but as an engineer point of you think, okay, individual component take about a single systems. What we are talking about is system reliability, whole system reliability, because one system, two systems, three systems are together, but you design a simple chip, one product, where your design has been poor. Okay, it means it is not reliable. But to compensate that, you have put another systems to make it available. Understand? So what we are talking about, a system point of view, complete system point of view, because system is reliable.
Sir, clear, sir. But
Okay.
as in whole system, though we are improving, but talking about a specific system, of course, the subsystems, it will not improve, sir.
Yeah, obviously. It's a very common sense also. Suppose you have many things. Okay, so as an engineer, you think if you are having four products, okay, both are unreliable, less reliable, okay, and you think that because availability is a user view, for you system is available. Okay, for you system is available, so you don't feel anything because reliability is a user view. Okay, but actually individual product is not reliable, but overall system is reliable. Okay, that's why there are three metrics has been given: RAM, reliability, availability, and maintainability. Let us take very simple way, industry point of view. I have one product. Okay, one product. I'm telling the reliability is very good, 99%. Oh, but its MTTR repair time is the, suppose I have a very foreign product. It is not failing, but once it fails, we can't repair in 1 hour. I have to purchase product from the Germany. So as a company point of view, industry wanted your system should be reliable, available, and maintainable also. If something goes fail, you can repair in 1 hour. Correct? Like that, I have a car, very good car, it is not failing in 1 year. Not your car is failing, like Maruti, suppose you're failing. But once you're failing, anybody you can go and correct and make it done in 1 hour. Any local people can replace it. All parts are available. So for you, availability become increased because even though it's failing monthly once, okay, but it is available. But I have a very foreign car. If it is failing, oh, part is not available in India. I place the order. After Germany, it will come. So in a year, one time it fails. But once it fails, for 1 week you have to relax. Correct? So that's why we are specifying three matrices: MTBF, MTTR, and availability. Correct?
Correctly.
Very, yes. Let us have a break. Then we will start actual topic.
Okay, sir. After break, we can take 2 questions which are written in the chat box.
Yes, definitely. We will take the question because I want to see.
Yeah.
So
we will start at 8:15.
Yes, 8:15.
After 10 minutes.
Yes, yes. Okay. Anybody can ask any questions. I can correlate with real life examples, and I don't want to rush that slides because there are many slides. I can give slides. Okay. Okay. And one more request. Depending upon your industry, somebody from mechanical, somebody from electrical, somebody from software. Please, all questions are welcome. I try my best to answer your questions, and I correlate with some industry. Okay. Let us wait for 10 minutes. Okay. Sir, please allow me for 10 minutes break.
Yeah, sure, sir. Please.